So it's great pleasure to have Sunghyuk Park from Caltech, but physically in Korea. He's going to tell us about three-manifold Q series and topological strings. Please.
Okay. Thank you very much for the introduction and also inviting me, giving me this opportunity to talk. It's a great honor and pleasure. So today, in this talk, I'm going to aim to give a gentle introduction or overview on z-hats, which is a three-manifold invariant coming from the three-dimensional theory T of y with n equals 2 supersymmetry. Along the way, I will discuss some recent developments that I was involved in based on this paper, and especially this last one was joint with Tobias Ekholm, Angus Gruen, Sergei Gukov, Pyotr Kowarski, and Pyotr Slavkovsky. Also, since I'm aiming this talk to be a gentle overview, please, at any moment, if you have any questions, please just unmute yourself and ask questions. So in the first part of the talk, I'm going to explain a little bit about the physical background. And then in the second part, I'll explain some mathematical approaches to define z-hat. And then in the last part, I will explain its connection to topological strings. So part one, physical background. So throughout this talk, we're going to use y as a symbol for our three-manifold. So starting from the 60, 0,2 theory on y times R3, and reducing it on this three-manifold y, the resulting theory is denoted by T of y. And for a generic three-manifold, only 4 supercharges are preserved, so it's it has n equals 2 supersymmetry. From the M theory point of view, it is the same as thinking of a system where the space-time is the cotangent bundle of y times c times r, with n number of M5 branes wrapping the zero section y times the origin times c times r. And here, c squared is the top knot space, which is a circle fibration over R3. So it carries a natural U1 symmetry rotating those fibers, and we're going to denote it by U1Q. And this origin times c sits inside this top knot space as a sort of a cigar inside it. So this theory, T of y, should really be thought of as a theory-valued invariant of three manifolds. And in fact, many invariants, old and new, factor through this theory, T of y. So diagrammatically, here, starting from a three-manifold y, through these, but by reducing the 60 theory, we get this 3D n equals 2 theory. And we can put this on various backgrounds, various three manifolds, and you can choose various gauge groups and so on. So for instance, if we use U11 supergroup as our gauge group, then it is known that the corresponding partition function we get is related to the Zarley-Witten invariance of three manifolds. And it's known that the supersymmetric, the space of supersymmetric vacua is the moduli space of flat GC connections on Y, where GC is the complexification of G. And also here, Z hat, it's a certain, it's a half index of this theory that I'm about to describe, and it will be the main character throughout this talk. So z hat is the half index of this theory, T of y, on C times S1 with a certain choice of boundary condition B at the infinity of C. In other words, if L0 is the generator of the U1Q symmetry, then Z hat is the trace, is the twisted Witten index. It's a trace of -1 to the fermion number operator times Q to the L0 over H curly HB, where this curly HB denotes the BPS sector or the Q cohomology of the Hilbert space. Since it enjoys this U1R symmetry as well as U1Q symmetry, it is naturally bigraded, and so it can be written as this graded Euler characteristic of this bigraded space of BPS states. So this setup is well known to be closely related to Chern-Simons theory. And let me just mention this conjecture by Gukov, Putrov and Vafa, relating this this half index z hat with the Chern-Simons partition function. For simplicity, let Y be a rational homology sphere, meaning the first homology group of Y is torsion. And we also set n equals 2, so we're using, say, SU2 as the gauge group. Then the Witten-Reshettikin drive invariant, or the Chern-Simons partition function of Y, say with level K, can be decomposed into a certain linear combination of the Q going to e to the 2 pi I over K limit of Z hat. More explicitly, this WRT invariant, or the Chern-Simons partition function, equals some normalization times summation over A and B, where A and B are elements of the first homology group of Y modulo Z2, which is the vital group. And here's a factor of which is the Chern-Simons action. SAB is a certain canonical matrix that's very explicit and determined just by the linking pairing of Y. Basically, it's determined by those homological information of Y. It does not depend on K. And here is the most important piece, which is the limit of Z hat as Q goes to one of these roots of unity. From a mathematical point of view, I think there are at least 2 takeaways from this conjecture. The first is that the WRT invariants, well, recall that WRT invariants are defined at roots of unity. So in this figure, if this is the unit disk, then along this unit circle at all the roots of unity, there's an associated WRT invariant. So a natural question would be, how do we unify them into a single invariant? And one approach to unify these WRT invariants, initiated by Lawrence and Zagier, and also from this works followed by Hikami, is to find an analytic continuation. So actually, in Lawrence and Zagier's paper, they found this analytic continuation in case of the Poincare homology sphere, and so on. But this conjecture by GPPV says that basically that we should, if we were to analytically continue WRT invariants, then we should decompose it first into several blocks, and then analytically continue each of them, because if our three manifold is not, it has a non-trivial first homology group, so that there are multiple labels B, then this conjecture suggests that we should first decompose it into some number of pieces, and then it can be analytically continued inside the unit disk. Secondly, this conjecture also says that these analytic continuations must be categorifiable, meaning that they are graded Euler characteristics of a certain bigraded vector space, curly H, B. In particular, they have integer coefficients because their coefficients are dimensions of certain vector spaces. So in low-dimensional topology, especially in quantum topology, some of the most important invariants people study are the Jones polynomials, which are the expectation values of the Wilson line operator in the Chern-Simons theory, and there's Witten-Resch ticket-derived invariants, which are the Chern-Simons partition functions on three manifolds. About 20 years ago, Havanov found an invariance of knots and links, which are valued in bigraded vector spaces, such that its graded Euler characteristic recovers the Jones polynomial. So, it turns out that Havanov homology is a much stronger invariant than the Jones polynomial, and it has been a very useful tool in study of 3- and 4-dimensional manifolds. So a natural question would be whether there is a 3-manifold analog of Havanov homology. I mean, if there is one, then that would be, then that could possibly be a very strong tool in studying this low-dimensional topology. And this Z hats and its categorification, which is the space of VPS states, they provide this possible candidate for this analog of Havanov homology for the 3 manifolds, in the sense that Z hats, they can be thought of as a decomposition of WRT invariants, and they are categorified into this space of VPS states. So that was the first part. Are there any questions so far? If not, let me continue. In the second part, I'm gonna discuss some mathematical approaches to Z hat. When the 3-manifold Y is simple, such as the 3-sphere, LP1 lens spaces, or some circle bundles over Riemann surfaces, then there's known Lagrangian description of this T of Y. And using that, in their paper, Gukov, Putrov, Vafa, they directly computed Z hat in those class of 3 manifolds. In general, however, we don't have Lagrangian descriptions of T of Y. So we can't do the computation directly. But instead, what we can do is to try to define Z hat mathematically from its expected properties. So in order to discuss this, it would be useful if we first review how we describe 3 manifolds mathematically. So this is a classical theorem by Licorice and Wallace from, I guess, the 60s. And this theorem says that any closed orientable 3-manifold can be obtained by performing a Dehn surgery on a framed link. I'm gonna explain what Dehn surgery means in a moment. And also the theorem of Kirby says that any two Dehn surgery descriptions of the same three manifold are related via a sequence of Kirby moves. So any Dehn surgery description consists of a knot or a link, say in S3, along with some numbers, either integer or rational numbers, associated to each component of the knot or link. So in this example, I have this figure 8 knot, and let's say there is the number p over q labeled on this knot. So what we do is we first drill out or cut. We first remove the tubular neighborhood of this knot. So we get this complement of the knot, which is a 3 manifold with a torus boundary. Now, by gluing a solid torus along the boundary of this knot complement, we can get a closed 3 manifold. And the way to glue the solid torus to this knot complement is described by this this number p over q. Basically, we glue the meridian of this solid torus to the p times the longitude plus q times the meridian of this knot complement, and the resulting closed 3 manifold is called the p over q Dehn surgery along the knot K. So the theorem of Licorice and Wallace says that any 3 manifold can be described as a Dehn surgery on a link. So instead of trying to visualize like 3-dimensional spaces, we can just imagine a knot or a link inside S3, which are labeled by these some integers or rational numbers. So what I drew here in the bottom is a Kirby move, or rather a variation of the Kirby move. So suppose you have a Dehn surgery description where one of the component is an unknot, and it's labeled by either +1 or -1. Then we can remove this component at the cost of putting either -1 or +1 full twist to all the other strands that passes through it. And then it turns out that the resulting 3 manifold that we get as a result of the Dehn surgery remains the same. And the theorem by Kirby says that whenever we have 2 Dehn surgery descriptions of the same 3 manifold, they can be related by a sequence of such moves. So in other words, 3 manifolds are the same thing as framed links, or just those links labeled by these numbers, modulo Kirby move. Here I drew a few examples. S3 is the same as having no surgery at all, but it's also the same as doing a +1 surgery or a -1 surgery on the unknot. It doesn't change S3. Here, the second example is the what's called the Poincaré homology sphere. It's the quotient of the S3 by a finite group of order 120, and it has various surgery descriptions. One of them is this one. So here I drew a graph, and this graph should be thought of as representing a link with 4 components. So each vertex represents an unknot, and whenever 2 vertices are connected by an edge, we link these unknot components in the simplest possible way. So basically in this picture, as in this picture, whenever we have a graph whose vertices are labeled by some integers, then we should really thought of them as a corresponding link. So anyways, so Poincare homologous sphere can be described either in this way or as this, or by this E8 Lincoln diagram looking plumbing. Okay, so so these three manifolds are this is a particularly nice class of three manifolds because they're associated to labeled trees. Those trees whose vertices are labeled by some integer numbers, and these are called plumbed three manifolds. It's a theorem by Neumann that any two labeled trees give the same three manifold if and only if they are related by a sequence of Neumann moves, which I drew here. So in other words, Neumann moves are the analog of the Kirby move if we restrict our attention to this class of three manifolds. Now, let M be the linking matrix of the labeled tree, gamma, and suppose M is negative definite. Then GPPV, from their paper, they say that the z hat for this three manifold can be computed in this way. Although this whole expression may look a little intimidating at first, this is actually very simple. So this contour integral, okay, there for each vertex of the graph, there is a variable x sub v, and by doing this contour integral, it simply means that whatever is inside this whole bracket, what we're doing is we first expand this whole thing as a power series in x, and then this contour integral just picks out the constant term of this expansion. And inside this parentheses, there is some factor, some products of rational functions on these x variables, and it is multiplied by a version of theta function associated to the lattice of which is determined by this linking matrix M. Here, M, the negative definiteness of M ensures that this theta function is this quadratic term, the power of q, is positive definite, which ensures the convergence of this expression. It's a theorem that this expression is invariant under Neumann moves. Therefore, it really is an invariant of three manifolds of this class. There's a negative definite plumbed three manifolds. Here I wrote one nice example. It's a three manifold, which is a Dehn surgery on four-component link, as drawn in this picture. And if we compute this z hat according to it, okay, by the way, this three manifold has has trivial first homology, so there's only one block. So we just omitted this label B here, and we get a nice Q series, which can be written in the compact form like this. So so that was all good. Plumbed three manifolds are, it's quite a big class of three manifolds, but at the same time, it's not too big because any plumbed three manifolds are not hyperbolic, whereas most three manifolds are hyperbolic. So how do we compute z hats for more general three manifolds? An approach suggested by Gukov and Manolescu is to use surgery or cutting and gluing. Basically, they suggest to study like z-hats for complements of knots and links first, and then study how to glue pieces together. And the idea is that z-hat should be a 2 plus 1 dimensional TQFT decorated by spin C structures. So remember there's label B. That appeared, they are understood as spin C structures. Okay, there's a lot of information in this slide, but let me try to break it down and try to explain things in this slide. So they conjecture that for each knot K in S3, z-hat for the knot complement, which they denote by F sub K of X comma Q. It's a 2-variable series with integer coefficients such that up to some normalization, if you set Q to be e to the h bar and you expand it into a power series in h bar, then the resulting power series is the same as that of the colored Jones polynomials when you set Q to be e to the h bar and x to be e to the nh bar. So the colored Jones polynomials are simply expectation values of the Wilson line operators along K. If we use if we color the Wilson line with the n-dimensional irreducible representation of SL2. So from this relation, in a sense, Fk is an analytic continuation of the colored Jones polynomials in the color variable. So there's, I guess, one thing that I should explain. So this x, we didn't have this variable for closed through manifolds. So why do we have this? Well, there's at least 2 different ways to understand this. The first is that, remember, z-hat had this additional label B, which parameterizes the spin C structures. And in case of knot complements, because the first homology group of the knot complements is always Z, there's a Z worth of different spin C structures, and X can be thought of as a variable that's dual to those spin C structures. Another way to think of this X variable is from the context of complex Chern-Simons theory. From complex Chern-Simons theory, this X is basically parameterizes the boundary condition of since this knot complement has a torus boundary, we need to specify the boundary condition, and this X can be thought of as the one parameterizing the boundary condition, and X is the Holonomic eigenvalue along the meridian of the knot. Yeah, in the context of complex Chern-Simons theory, we often use variable X to denote the Holonomic eigenvalue along the meridian, and variable Y for the Holonomic eigenvalue along the longitude of the knot. They also conjecture that this Fk should be annihilated by this A hat operator, which is known as the quantum A polynomial. So this is a non-commutative polynomial in X hat and Y hat, which are Q commuting. So for those who are not familiar with this quantum A polynomial, you can just think of it as a quantized version of the moduli space of flat SL2C connections on the knot complement. So in the same paper, they compute Fk for torus knots, as well as the figure 8 knot, which is the simplest hyperbolic knot. In addition, they conjecture that this following surgery formula, let S3 sub P over R of K denote the P over R surgery on K. Then there's this formula for the Z hat of the corresponding Dehn surgery through manifold. As you can see, this is more or less in the same form as this previous formula that we've seen, because we have this contour integral. Basically, it picks up the constant term of whatever is inside this parentheses, and we have this version of theta function here. And here we have fk, and this additional factor can be thought of as coming from the solid torus that we are gluing in. Here's a small issue here, because this right-hand side does not converge always. It only converges provided that minus r over p is big enough. So, and their conjecture says that whenever this minus r over p is big enough so that this right-hand side converges, then this should be true. They actually give this quite a remarkable example, which is the -1 surgery on figure 8. Topologically, it is the same free manifold as +1 surgery on the left-handed trefoil. So from these two different surgery descriptions, we can compute Z hats, and you see that they coincide as expected, which is given here over here. Like, so even though even though we expected these two series to match, I think it's still a very highly non-trivial check that Z hat really should be a TQFT. And by the way, as a side remark, this series is a well-known series. It's one of the 7th-order Mach theta functions studied by Ramanujan about 100 years ago. Let me now describe a bit about the use of R-matrix in the context of FK. Recall that colored Jones polynomials can be computed using R matrices from plumbed groups. And the crucial observation is that we can analytically continue these R matrices and the color variable. Under this analytic continuation, those finite dimensional representations Vn now becomes an infinite dimensional representation of Verma module V infinity with the generic Heist weight, and the Heist weight is parameterized by x. It is the same x variable that we've been using. So whenever we have a braid, say a braid going from the bottom to top, we can imagine that each strand of the braid carries this Verma module, and whenever two strands cross, like whenever there's a positive crossing, we can think of that there is we can associate this map, this V infinity tensor V infinity to V infinity tensor V infinity coming from the R matrix. And since R matrices satisfy Yang-Baxter equations, this naturally induces a representation of the braid group with m strands into the endomorphisms of the mth tensor power of the Verma modules. So we get an infinite dimensional representation of the braid groups parameterized by x. So to get a not invariant, we need to close up the braid. That is, we want to take the trace. However, due to the infinite dimensionality, taking trace is quite tricky because often the trace does not converge as a nice Q-series. Still, we can prove the following. For any positive braid knot, where positive braid knots are those knots which are closures of braids which only uses positive crossings. So for any positive braid knot K, if we can take the quantum trace, we can take the trace of the corresponding representation, and it converges well, and it gives the FK that we want. So positive braid knots and negative braid knots, they include all torus knots as well as infinitely many hyperbolic knots. So it gives us a huge amount of examples now for which we can compute FK. In the same paper, I also computed FK for double twist knots, Whitehead link, and Verma rings. Yeah, I drew an example of a double twist knot as well as Whitehead link and Verma rings. So yeah, from this we have quite a big playground where we can so for on these Verma rings, Whitehead links, we can do surgeries, and we've checked that like whenever we have two different three manifolds, whenever we have the same three manifold with two different surgery descriptions coming from these links, they give us the same same Q series.
I have a question.
Uh-huh.
So sometimes you have sometimes you have a cross form expression for FK. Sometimes you don't. For instance, here you don't have cross form expression, right?
Yes. So for figure 8, so they didn't write down a closed form expression in their paper.
Yeah, whereas you have some some double twist on like a 5-2, as far as I remember, you have cross form expression, right?
Yes.
But do you know where does difference come from? Even though it's the same double twist knot, sometimes it's easy to find a cross form expression. Some class it doesn't. It's not. It's really difficult. Do you have some insight?
Well, yes and no. So for these positive braid knots, what was important was that this positivity somehow gives us convergence. Positivity ensures that those Q powers of Q gets a positive, more positive. And it's similar in case of those double twist knots. When we consider double twist knots, so double twist knots are parameterized by two integers, m and n. If m and n if both of them are positive, then it is easy to write down the closed formula. But figure 8 knot is like +1, -1.
Yeah.
And so it's kind of like in the context of this plumbed three manifolds, we require this negative definiteness in order to ensure convergence. But if it's not negative definite, then we need some additional techniques to deal with this indefiniteness.
I see.
I think that's and that's what's happening here. So yeah.
Okay, thanks.
Yeah. So before we finish this part 2, yeah. So as I just explained, we have a whole bunch of examples, and so even though we don't have a fully general mathematical definitions of FK and Z hat yet, I think we are certainly getting closer. And in the I also just wanted to mention that in the work in progress, so I found closed form formulas for all these knots and links, basically including figure 8 knot. I have a closed form formula for Borromean rings, Whitehead links, and any double twist knots. and also worked out some positive surgery formulas, which was previously a bit of a issue because we couldn't ensure the convergence, but I found some way to deal with it. Hopefully we can find definition soon, and I hope it can shed some light on the physics of T of Y as well. So that's the end of the part 2. Are there any questions so far?
So you have some cross formula for figure 8 and the Borromean ring already.
Yeah, I
oh,
do
okay.
that.
Okay, thanks.
Any other questions?
Oh, then can you obtain the z hat for like a T3, like a 3 torus? 3 torus can be obtained by surgery on the Borromean ring.
Yeah, we're doing 0 surgery on it.
Yeah.
So so far mostly we've been focusing on rational homology spheres, and 0 surgery is slightly different. So it was noted that so we were studying. I was studying with Chan, Sopenko, and Gukov. We were studying z-hats for plumbed manifolds where now the graph can possibly have loops.
Yes.
Yeah, and in those cases, we've observed that if we were to decompose the Chern-Simons partition function, then we not only get those blocks coming from the abelian flat connections, we also get additional blocks, which are coming from what we call almost abelian flat connections.
Yeah.
So things get more tricky here, and yeah.
I see. Depending on the surgery, it gets more difficult. Okay. It's not like a simple just Cantor integral you have written down.
Yeah. So you mean that this formula?
This formula.
Yeah. So this only works when this coefficient, when this negative of inverse of the coefficient is big enough.
Okay, I see.
And yeah, when for the 0 surgery, I mean, you can either think of z hat for the 0 surgery as just the first coefficient of the fk. So I mean, to give you an example, so if we consider the 0 surgery on, I forgot if it was, okay, if we consider the 0 surgery on the trefoil knot or the figure 8 knot, then then there are more than one blocks, and the one corresponding to the abelian flat connection is just the first coefficient of fk, which is just like 1.
Yep.
Yeah, and then there are more blocks. From it.
I see. Okay, thanks.
If there are no other questions, let me start discussing the connection to topological strings. From the physics point of view, this connection to topological strings is quite natural because the setup we've been using is also a standard setup for topological strings. Now, the equivariant parameter Q we were using is related to the string coupling constant by this Q equals e to the GS, the string coupling constant. Let me briefly review some dualities between the topological strings and Chern-Simons theory. So Witten in 1992 showed that Chern-Simons theory on Y can be viewed as the open topological string theory on the cotangent bundle with some number of d-branes wrapping the zero section Y. He showed this by taking the string field theory of this open topological string theory and by observing that it localizes on Y, and the corresponding Feynman diagrams are the same as the ones coming from the Chern-Simons theory. Now, let's take Y to be the three-sphere. Then Gopakumar-Vafa showed that in the large N limit, the geometry of this cotangent bundle of S3 deforms to the resolved conifold, what's known as the resolved conifold. It is the total space of O-1 plus O-1 bundle over CP1. And those d-branes vanish in this geometry. So this large N duality is a duality between this open topological strings and the closed topological strings on the resolved conifold. So combining these two dualities, the conclusion is that Chern-Simons theory on S3 is equivalent to closed topological string theory on X. Oogurl and Vafa also showed how to incorporate Wilson lines in this context. So in order to incorporate Wilson lines, we can put some number of probe branes wrapping a Lagrangian submanifold. It's known as the not conormal. Inside a T star S3, a not conormal is the set of points x, p, where x is a point on the knot, and p is a cotangent bundle. Sorry, p is a cotangent vector on that point x, which is orthogonal to the tangent vectors along the knot k. Of course, in this form, this not conormal lives inside T star S3, but we can slightly shift this not conormal off of the zero section, and then doing this geometric transition, I'm going to resolve conifold. We can think of this not conormal as sitting inside the resolved conifold as well. Since we've been talking about z-hats for the knot complements, we are interested in the case when Y is the knot complement. But it turns out this is a little tricky, and we're gonna use instead we're gonna use a simpler setup, which is we put n-1 branes on S3, put one probe brane on MK, where MK is the knot complement Lagrangian. It's obtained by performing a Lagrangian surgery on the intersection of LK at the knot conormal and S3. So this is a schematic diagram. If this line represents S3 and this line represents the knot conormal LK, then they intersect along the knot K. And doing Lagrangian surgery means that we remove a small neighborhood along this knot, and we connect these two Lagrangian submanifolds smoothly. And the resulting Lagrangian is called the knot complement Lagrangian because it is diffeomorphic to the knot complement. So we're using the simpler setup. It's a simpler setup because we're using only one probe brane. And in the context of Chern-Simons theory, having just one probe brane means it's equivalent to only considering symmetric representations of the gauge group. So in order to connect this to z-hats, I should talk a little bit about how to specialize to symmetric representations in the context of z-hat. So there are some formulas for z hat for negative definite plumbed through manifolds and torus knot complements for any complex simple Lie algebra. And for our purposes, we say let the Lie algebra to be SLN. And since those x variables were, like in the context of Chern-Simons theory, these were Polanyi eigenvalues along the meridian. And since it's SLN, there are n-1 number of independent eigenvalues. These are, because n-1 is the rank of this Lie algebra. So there are n-1 number of x variables. And specialization to symmetric representations is the same thing as setting x1 to be x1 x and setting all the others to be q. And we're going to denote it by symmetric SLN fk. In that paper, I also observed that this symmetric SLN fk is annihilated by what's called the A-deformed quantum A polynomial when this A variable is specialized to q to the n. In the context of topological string theory, this A should be thought of as the exponential of the complexified Kähler moduli. And here's a conjecture by Tobias Ekholm, Angus Gruden, Sergei Gukov, Fyodor Kuharsky, myself, and Fyodor Swarkovsky. So we conjectured that there exists a 3-variable function. Now there's an additional variable a, fkx, a, q, such that when we set a to be q to the n, then it becomes the symmetric SLN version of fk. Also, it should be annihilated by the quantum a, the A-deformed quantum A polynomial. And finally, from the physics point of view, this should be thought of as the topological string partition function in the setup we were discussing. That is, it counts the holomorphic curves on the resolved conifold with the knot complement Lagrangian in it. Let me describe one consequence of this conjecture. Let's write fk semi-classically since q equals e to the string coupling constant, we can write fk as the exponential of 1 over string coupling times the Gromov-Witten disk potential uk plus all the higher genus terms. And let's also let's say b hat is an operator sending this n to n plus 1, or equivalently, it's an operator shifting a to q times a. Then the expectation value of this operator, this b hat, at y equals 1 and a equals 1, is by definition the classical limit of the ratio between fk when a is shifted by q over fk. And it is 1 over the Alexander polynomial. It's because we know that the classical limit of the symmetric SLN fk is just the Alexander polynomial to the power of 1 minus n. But from this semi-classical expansion, we also know that b hat, the expectation value of b hat, is the exponential of the partial derivative of the Gromov-Witten disk potential by log of a. And since uk is integral log y d log x, it can be expressed in this form. And finally, it can be written as in this final line. So what we get from here, this manipulation is an expression of the Alexander polynomial in terms of this A-deformed A polynomial. And in the recent paper by Dehn and Ekholm, this was proven actually mathematically. Their proof uses not contact homology, and they were counting certain. They're studying the moduli space of holomorphic annuli, and in the same setting actually, the result conifold and with a not complement Lagrangian. Yeah, in this formula, this aug denotes the augmentation polynomial in the context of not contact homology, which is expected to be the same as the A deformed A polynomial. So that's all I wanted to say for about this part 3. Well, so this is, I would say this is all the beginning, and there's a lot more to study about it. Actually, in the work in progress, yeah, with the same group and also with Marko Stosic, we are studying FK for various other branches. Its relation to non-Scribner's correspondence, also the quantized Coulomb branch of the 5D 3D system. I mean, there are lots of interesting connections between different areas, and I think it's all very exciting. So in summary, in this talk, I try to convey what this interesting three-manifold invariant Z hat is, which can be given various physical interpretation. And many of its interesting properties are yet to be studied and discovered. Yeah, there are lots of connections between Z hat and, for instance, certain modularity properties, its connection to non-semi-simple MTCs, logarithmic VOAs. I haven't talked at all about these things, but there are a lot of interesting things going on. Hopefully, in the future, it will shed some light on the physics of T of Y as well, and the topology of 3 and 4 manifolds. So thank you very much for your attention. Are there any questions?
Thank you very much. Questions?
I have one question. First, thanks for the nice talk. And since the FK is like an analytically continuation of the Calder-Jones polynomial, I was wondering if it is possible that we can give a mathematical definition of FK, like scaling relation.
And yeah, that's a very good question. So I have thought a bit about it, and what you see is that if there were some scaling relations for FK, then it's probably an infinite term scaling relation. It's because if you think of, say, so the scaling relation for the usual Jones polynomial is a 3-term relation, and if you think of the scaling relation for the colored Jones polynomial colored by the 3-dimensional representations, it's a 4-term scaling relation. And if you think of higher and higher dimensional representations, the scaling relation has more and more terms. And so when as you go to the infinite dimensional representation, it is natural to expect that the scaling relation would be some sort of an infinite term scaling relation. But yeah, so we don't have much idea about it, but that's a very good question, and I think it's worth thinking about it.
Any other questions? So in the case of links, did you check its analysis by some recursion relation for FK?
So, well, I want to check, but I'm not sure if the corresponding A ideal, but the quantized A ideals, no. But instead, I checked for all the twist knot cases that are available. Yeah, but if you
not case, it's obvious, but for link case, it's not that straightforward.
Yeah, I mean, if there are some known quantum A ideals for those links, then yeah, then I'd love to check it.
Yeah, Hopf link it's known, like for torus link.
Oh, really? Is it?
I think so. Yeah.
Okay, then I should check it.
Okay.
And I think it will be. I mean, it must be annihilated, but I think it's
Okay.
still worth checking.
I see. Okay. Okay. Another question is, so this, you said quantum Coulomb 5D, 3D at the end, right?
Oh yeah.
I just wanted to know how this, I mean, is it related to A hat? Do you mean this?
Yeah, so
A hat
yeah,
which annihilate FK?
So what we study in this work in progress is that, so one of the things we observe is that these FK, they not only satisfy the Q difference equation coming from the A deformed quantum A polynomial, they satisfy Q difference equations with respect to the A variable.
No.
So remember I denote here by B hat. So this B hat is a variable that is dual to A. And they Q commute. So they also generate the quantum torus algebra. And so actually there is not just quantum A polynomial, there is actually a whole ideal.
I see.
And that's the quantized Coulomb branch, the system. So it's a coupled open and a closed open. Yeah, I mean, it's a system where both the closed string moduli, open string moduli, they're coupled together. Because X is supposed to be the open string moduli and A is supposed to be closed string moduli.
I see. I see. Any other question from audience? Okay, if not, let's thank the speaker. Thank you very much. And I will stop recording.